Hey everybody, Dr. A here, and in this video we're going to be exploring some background information on the simplification of force and couple systems for the sake of a statics course. Now, as I've said in some of my other videos, it's a good idea to have a good textbook handy. In my case, with a lot of my statics videos, I'm going to be kind of going along with the Hibbler statics textbook and kind of referencing sections in that particular book. So when it comes to this particular topic, simplification of force couple systems, one of the interesting things about this is that later on in later courses and in engineering practice, we typically don't see simplification of force couple systems by itself. Typically, the simplification of force and couple systems is part of a larger, more complex analysis process. But in order to explore those more complex analysis processes later on in more advanced topics, we've got to get this key process of simplification of force couple systems under control, which is why we kind of devote specific attention to this subtopic. So that's the purpose of this video, and then we're going to have some accompanying examples along with it. So make sure you hit like and subscribe and be on the lookout for content like this and all kinds of other engineering content on my channel. Thanks for watching, and let's go ahead and get started.
In this video, we're going to be giving some background information on what's called the simplification of a force and couple system. So basically, what we're looking at doing is taking a loaded system and replacing the system that may have forces and or a couple moments acting all over it, and drawing what's called an equivalent system that has one single equivalent resultant force and one single equivalent couple moment that is statically equivalent to the original system. Okay, so we'll make a note here. We're going to say replace a system of forces and couple moments by an equivalent system of a single resultant force at a specific point and a single resultant couple moment at the same point. Okay, so basically what we say is we're going to say we're going to develop an equivalent system. That's what we kind of summarize that as, developing an equivalent system. So we're going to look at a couple of quick illustrations in this video, and then we're going to get into some examples. Okay, so let's look at some two-dimensional illustrations first. Okay, so the simplest illustration I can show you is if we have what's called a cantilever beam, which means you have a very rigid connection. It's fixed on one end, and you have the opposite end is sticking out as free. And let's say that that's supporting a point load F at the end, and then let's say that the length of this member is L. Okay, and I'm going to call this point on the left end, I'm going to call it point A. Okay, so what would an equivalent system of this be? So let's write this here. We're gonna say draw the equivalent system. So look at the definitions we put up here. We said we're gonna replace a system of forces and couple moments. In this particular illustration, we just have a force. We don't have any applied couple moments yet. But we're gonna replace this by an equivalent system of a single resultant force at a specific point. In our illustration, our specific point is point A, and a single resultant couple moment at the same point A, and that's what we call this equivalent system. So what I'm going to do is I'm going to redraw this beam here, and it's the same beam, okay? It's the same, geometrically the same. It still has length L. And what I'm able to do is I can say that this equivalent system would be if this force was translated to this fixed connection, same magnitude F, and I translate and place a moment right here of m equals F times D. And again, this is point A right here. All right. Now let's take a second and think about what this implies. So what we're saying is at point A, at a point of interest, in our case at point A, what is point A feeling? That's one way you can think about this. What are the effects that point A is feeling here? Well, point A is feeling the effect, the actual effect of the vertical force here. That's why we're able to put F over here. But what else is being felt at point A? Well, this force is causing a moment about point A, correct? I mean, force times perpendicular distance. So a moment is being generated about point A. So not only is point A feeling the effect of a point load here, call it F, but it's also feeling the effect of this bending mechanism right here, M, and that's equal to force times perpendicular distance. And that would be, this would be the equivalent system that is statically equivalent to this first system I drew here. Let's do another illustration real quick, okay? And hopefully this will maybe solidify your understanding, okay? Let's call this another original system. And I'm gonna, in this system, I'm gonna make another cantilever beam, and I'm gonna call this F1, and I'm gonna call this F2, and I'm gonna call this total length L, and I'm going to say F2 is at the halfway point, L over 2. Okay, so if you want to, you can put the whole length here as well, L. So I want us to draw an equivalent system. I'm going to call this point B. So I'm going to say let's draw an equivalent system of loading at point B in this case. All right, so again, similar to what I did before, I'm going to redraw the geometric, the beam itself in terms of its geometry. Here's point B, okay? And instead of having F1 and F2 out here on the beam, the equivalent load that B is feeling, ask yourself, what is point B feeling? Well, point B is feeling some resultant force, F sub R, that's equal to F1 plus F2 going down, right? So let me actually move this over just a little bit. Okay. And then I would draw that right here, okay? F1 plus F2, okay? What else is it feeling? Well, remember, both F1 and F2 are generating a moment about point B, a counterclockwise moment about point B. So I'm going to draw a moment here. I'm going to call it M sub R for resultant moment. And what is that moment going to be equal to? Well, it's going to be F1 times L, right? F1 times L. And then it's going to be equal to plus F2 times L over 2, right? F2 is here times L over 2. And this is what we call the equivalent system, right? We have replaced the loading on the original system with an equivalent single resultant force and an equivalent single resultant moment acting at a specific point. So again, the question we ask ourselves is, what is this point feeling due to the effects acting somewhere out on the beam? And this is what it's feeling. Now we can extend this into 3 dimensions. It's the same concept, but in 3D. All right, so what about in three-dimensional form? Okay, let's just say that I have this arbitrary body. So we often draw that as kind of like a blob shape of some sort. And let's say that we have a point of interest. Let's just call it point O right here. All right. And let's say that we have an F1 acting right here. And then maybe we have an F2 acting right here. And what if we have like a couple moment acting right here as M vector, okay? M vector. So by the way, I know this doesn't really look like a very nice 3D drawing, but this line of action right here, this is the axis that my moment is rotating around, okay? So you can think of it as this little vector is going through the curl of this moment, all right? And so this is our arbitrary body, and what we're going to call this the original system, okay? And I want us to draw an equivalent system. Draw an equivalent system with loading at point O. All right, so we're gonna have the same kind of arbitrary body here. Let's see if I can nicely reproduce that shape. Okay, it's close enough, right? And here's point O. All right, and so what we do is the first thing we need to do is we need to recognize that these forces, these Cartesian vector forces, are causing a rotation about point O, right? They are going to have a position vector associated like R1 and R2 right here. Do we care about the position vector for M? Not really, because it's already a moment. All right. So how do we write this equivalent system? Well, at point O, what we're going to have here is we're going to have our forces translated over. So we're going to call this F1, and we're going to call this Cartesian F2, okay? And then we can translate this moment over to point O. Same moment M. All right. Now, when we have translated this over, you got to keep in mind that that because F1 and F2 were at a distance R1 and R2 away, you have to account for the effect of bending that it's having, that each of these forces are having at point O. So I'm going to need to further draw the equivalent moments caused by F1 and F2. So I'm going to call this right here, how about I call this M1, and how about I call this over here M2, okay? So this becomes kind of our equivalent system. And then we can then say that a resultant couple moment is equal to M1 plus M2 plus that original M that we drew that was just acting on the original body anyway. And then we have a resultant force equaling, F1 plus F2. So finally, the final equivalent system is going to look something like this. This is point O, and we have some kind of F resultant here, and then we're going to have some kind of M resultant here that incorporates all of these effects together, okay? So again, in general, we would say a resultant force is equal to the sum of all of the individual forces acting on the system, and a resultant couple moment is equal to the sum of all of the moments acting on a particular system. Now, in 3 dimensions, again, it's the same concept as 2D. And I'll go ahead and tell you the textbook has much better figures and drawings in the textbook than what I was able to reproduce in this video. I am not an artist by any means. So for some better graphics, take a look at, I believe it's section 4.7 of the textbook. Okay, in fact, let's put that up here. This is section 4.7, okay, of the textbook. And it's got a nice longer explanation and figures to show you the representation of it.